Hello everyone, welcome back to AWS Well-Architected Solutions on Twitch. It's great to be back with you guys talking about the architectural best practices and well, let's jump right into it. I'm Julio, I'm a Technical Evangelist here at AWS. This means that my job is to be here helping you software engineers be successful with our chosen products. So the hard part is each one of you's got a different view on that, different challenges, and that's why this well-architected framework is designed in a way that it's not tied to any specific workload and should be useful for everyone, because we're going to talk about operational excellence, security, reliability, performance efficiency, and cost optimization. And I believe those topics are very important for all of you guys. So that's what we are running in this series. And specifically in today's episode, we are going to be looking at reliability and scaling. So let's take a look at my desktop. We can change to this document, and if we take a look at the well-architected framework, each of those pillars is divided into several best practices in the form of questions. And for example, in reliability, we already discussed how to manage AWS service limits for accounts. We've done uh, planning network topologies, and now we are talking about how to evolve your system, especially in the scaling sense, how to adapt to changes in demand. So elasticity is the key word that we've been working on in these two aspects. First, defining the constructs to make your application scale in each of the services where this may happen. So we are talking about instances or functions or containers or databases. Each of those will scale a bit differently. So we are taking a look into to each of those areas, and make sure the workload is load tested. So we are checking out a few tools such as JMeter, Gatling, and other things to help us do our load testing. So that's it from the AWS part of things. We're going to take a look at a lot of code today, and that is all shared with you guys here on this GitHub repo. It's mine GitHub for now. It's fairmanj/sitting ducks. And every line of code that I show you guys today is totally committed to this repo and tested here. And this is growing as we continue in this series. And all those days, each episode, we add a few templates and scripts in this repo. Okay. All right. So I can see there are some of you on Twitch chat already on the stream. Glad to be with you guys. Please, if you have any questions at all, feel free to ask on Twitch chat, or if you are watching this recorded afterwards, you can get in touch with me on GitHub. It's FairmanJ. At Twitter, it's FairmanJ and FairmanJ at Amazon.com as well. I would be happy to continue this conversation with you guys at any time at all. But taking the advantage that we are live together here, feel free to just use Twitch chat. And the way we are building this is progressively. So we have a few CloudFormation stacks already built here that we've done in past episodes. So we'll do a very quick review of what we've done so far. And we've done instances on Beanstalk. We've done functions on Lambda, and now today's topic is containers with Elastic Container Service, and it's in its two flavors, EC2 containers and Fargate containers. So we're going to talk a bit about that. And well, let's jump right into it. So I have the repo cloned here in my machine. So as this is a Docker episode, I already have my Docker file open here. But before we get into Docker, I will review very quickly what we have in the rest of the stack. So we begin very simply by creating this CFN artifacts stack with this shell and the related CloudFormation template. And this is the way I organize my code, and everybody does this a bit differently. Every context may have its process and best practices. But if you like it, this is how I do all my projects, and you may take a few ideas from it. So the CloudFormation template here, it's very simple, just a minimal CloudFormation thing you can think of. If you're new to CloudFormation, you can see that this is our main tool for infrastructure as code. So here I'm declaring in code what I want my infrastructure on AWS to be. So in this case, I'm creating a bucket on the S3 service, our storage service. And I'm not only creating a bucket, I'm receiving a parameter, and I call this parameter gallery ID. And in this template, it's not doing much, it's going directly to the output. And in the output, I'm exporting this value as a reference called the gallery ID. And gallery ID here means just the same as you would call an environment, such as production or dev test or homolog or pre-prod or whatever you call your environments. But environment is a bit of a overloaded word. We have beanstalk environments and things like this, so I don't want to have um, conflicting names, so I call this galleries instead of environments. And that's just this, because I can have several of those. Like if I have 10 environments, each one of its with its own bucket, I can prefix with the environment name, and I have a naming standard, like a good naming convention that I can use to reference elements between one stack and another, because this is what this export does. It will export this name. It will be like dev test colon artifacts buckets name, so that in other templates I can import this value, and the CFN artifacts will create just that. So, and a few tricks here that we've talked about in the previous episodes. We can query the results of AWS commands that we run on the CLI to create these stacks or to describe these stacks and things like this. So if you want to create this, let's take a look at what this shell script is doing. I'm generating a unique ID for my environment, using it to create this gallery ID that I was talking about. In this case, it will be just devenv and the unique number and the gallery and component ID. So when I call create stack, I pass the parameter, the template body, and wait for the stack to complete. And that is just that. And the same idea holds true for every AWS resource. So when I create this in CloudFormation, this is our resulting stack. I've done this in each and every episode before, so this is getting a bit boring by now, but if you create from the repo, you should have the exact same result. I don't need to do this again. And on the outputs tab of your resource, you're gonna see that we have the bucket created, the actual name of the bucket that was created was generated automatically. And this is a very important part, the idea that treat resources like cattle, not pets. Or, as my vegetarian friends prefer to say it, treat like disposable cups and not your cherished mugs, right? So you can just throw them away and reuse it as convenient for your scenario, not something you have to take care with all attention. So letting CloudFormation generate the names helps you to not care so much about them. And in the end, the export name that may be used to reference this bucket in other stacks is dev.env, and the name of the stack, and the artifact bucket name. So yeah, uh, well, these videos that we are doing on YouTube go on Twitch. They go to YouTube after a while, so you can, my friend Q Trill Labs 1 and Fullness on 14. You will find that afterwards, both on Twitch and on YouTube. And well, the query is a bit of a hack, my friend Sutinki. But it's a very important hack. Like the query, I'm getting the bucket name from the stack that was created. So the idea is showing how in a shell script I can pass parameters and fetch outputs. So I'm taking from the first stack the output in which the key is called artifact bucket's name, and from that getting the output value, which is exactly this value here. So this is just to get parameters in and out of CloudFormation to and from shell scripts, and that's a nice hack. And well, this is for the bucket, and this is just to store our code and artifacts and things like this. More interesting would be the base AJ VPC stack, and the base AJ VPC is just a virtual private cloud, like a network block, divided into 4 subnets. Why 4 subnets? Well, because we need, for high availability, to have them in separate availability zones. Everything that we have in one AZ, we have to have in another. So we have 2 public subnets and 2 private subnets. That's there's people who do 3 AZs, 4 AZs, depends on what you have available on your region, and this may change a bit, but more than one is certainly very desirable. And let's take a look at that template. And and its shell script. So we can see that this is very straightforward. Just set the CIDR blocks and create the AC2 VPC, create the subnets, and here it is very important to see the properties. Like, how do you know what those properties are and what they do? Everything is on the CloudFormation docs, and they help a lot in finding out how to declare this, because you have examples here, and you can see, for example, the CIDR block property is the CIDR block for the VPC you want to cover. It is required, it is a string, and if you update it, it will need to replace your VPC. And this is quite important to understand what CloudFormation will do when you change this value. For example, if you change the enable DNS support property and deploy your stack again, this is not required, it's a boolean and requires no interruption on your stack. So this can help you understand when things would stop or be replaced or continue with just a config change, right? And this is just to set up the network. So this is the environment VPC, And again, this little trick here, get AZs from the region and get the first, we'll get us in the first AZ, and doing the same thing with an index of 1 will get us to the second AZ on the region. And so we guarantee that those two subnets are not in the same region. This for the public subnets, same thing for the private subnets here. So then for a network to be public, it's got to have an internet gateway, and the internet gateway needs to be attached to the VPC. So here's how you do it. The routing tables, public routing goes to the internet, everything else is internal, and so on and so forth, binding the subnets to the routing tables, net gateways, so that the internal networks instances can go out to the internet from network address translation. And that's our network infrastructure. And well, to be honest, I'm talking about other options for declaring CloudFormation templates and other infrastructure as code tools like Troposphere or Terraform. There's certainly a lot of discussion there, and some things the that CloudFormation does that none of the others do, and something that the others do and none of not and that CloudFormation does not. I'm not a huge. I've used those tools in the past, both Troposphere and Cloud and Terraform, but I will show you guys that the thing about CloudFormation is it's not only text. It's not only declaring how things are, but how they relate to each other, and the composition that CloudFormation offers today. I don't see any other tools like to bind the life cycles with nested stack and cross stack references and stack sets. This kind of thing is very important for a complex architecture, and I don't see a lot of that in other tools, but that's of course my preference. And being AWS, that's what we focus on this, and I can ensure you that it's just two different ways of getting to the same results. And if there is anything that you would like to see how to do on CloudFormation specifically, you can just ask and I will cover it. Okay, so the this is the network definitions then, and you can see the same pattern here. The every ID, everything that I want to reference in other templates, I export. So this gallery ID is the VPC ID, the ID of the subnets, and everything is exported by CloudFormation. So here in the CloudFormation console, in the base AJVPC stack, you can see here the same dev env and each of those values and the export names and the values that they have. So that on the first episode in the series, we did Beanstalk with regular instances. So very the closest as possible as you would have on your traditional application server, or if you are already running on the cloud, perhaps you're already using Beanstalk. And when using this, when creating the Beanstalk environment, you can import the values from the other templates. So when I do this, let's take the subnet definitions. So here in this namespace property, AWS EC2 VPC, subnets, I'm telling Beanstalk that I want to use my subnet A ID and my subnet B ID under this gallery. And again, this gallery ID is just a hack, so I can have several environments and not clash them. So I can have unique IDs and reference any amount of stacks that I'd like. But it could be just a simple string. This is a bit of one way of doing things. If you don't have many stacks at the same time, maybe you don't need it. But I highly recommend that it helps me a lot that when you use cross-stack references, you have a consistent naming standard. Like this one is what I use, but anything should work just the same. And this is how this stack came to be on Elastic Beanstalk. And what application is that? Like when I hit this endpoint URL, like when I hit this code, what's happening here? So I have this bundle, the source bundle, pointed to my Python app. And here in my Python app, you will see that it's very simple. It's just a Fibonacci app, like just calculating Fibonacci sequences. And I have a few of those, a few different methods. So we have different compute types, and we can play with it a little bit. But this is the Fibonacci with generators, the Fibonacci with memoized functions, recursive implementation, iterative implementation, and it's the same function. Every deployment that we are doing here, it's the same Fibonacci functions. And in this series, we are going to dive deeper. Of course, this is just compute, but in the next episodes, we're going to add databases, message queues, in-memory caches, log storage, and whatever you guys think it's interesting. We are starting with scaling in compute, but this is growing in complexity as you can see. So this is Beanstalk, and Beanstalk is pretty simple to deploy, but not so simple when you go to scaling, because there's a lot you have to define, and we're going to see what those issues are. Here in this Beanstalk app, as we've done it in the first in this first episode, the scaling part was defined as Beanstalk properties. So here in the source main Python resource, where's the .eb extensions? I think VS Code is probably hiding me something here. The EB extension resources that I have, let me find it on the console, or it's .eb extensions. No, where are those guys? Well, I'll have to find that for you guys later. But the idea is that you have to set up by hand what are the alarms and everything that we set by hand, like when do you want to scale up, when do you want to scale down, what are the auto-scaling policies, and things like this. And recently we've been talking a lot about serverless because that's much simpler. If we take a look at the serverless stack that I have defined here, I just tell for each function that I have on my code, I bind them to a handler. So on Beanstalk, they were all being served by Flask. So I have a Python running with Flask and managed by me. Here it's managed by Amazon. So I don't deploy the package, I deploy the functions specifically. So here I deploy one of them, the iterative version. Here I deploy another one, the recursive version. Here the memoized, and so on and so forth. And I put each of those behind an API. So one different path in the get method, they will have each one their own REST API. And in the end, I can export the target so you can hit those functions as they go. So that's the, again, a flavor of CloudFormation. CloudFormation will use these serverless transformations to transform this AWS serverless functions in Lambda functions with much more properties and things like this. So We are talking about a bit of two extremes here, extreme cases, because on this one, on the function side, we have to, we don't have a lot of control, like what is in this machine, what is on this instance, how is it going to run, how is it going to scale up. Um, Amazon will just provision as many executions of these functions as you have calls, right? Um, and there's about so Demo about good starting points and documentations for S3 Node and React. Take a look at the video section on the Twitch channel right here. A couple days ago, Nikki and AM just did a stream covering just that. If you go to aws.amazon.com/developers, you will find that their code, and right here on the videos tab, you can see them going through it, and they do exactly that. A single page web application hosted on S3, and they're using Angular in this first one, but React would be pretty similar. Definitely check them out. But today is about containers. So let's go to that, because in serverless, you don't even have access to the container. You just deploy your function and go. But perhaps you would like more control, but not so much as to go down to managing your own instances. So I believe containers can help you balance this abstraction level, have some control on your operating system and how your software runs in more details than you would be able with serverless, and at the same time having some convenience and trade-offs to make it not so complex as managing everything yourself. So that's what we would be trying to achieve today. So if we are trying to build a container-based app and deploy container-based apps, the first thing to create is a Docker file. So here in this Docker file, I'm defining my app. So I'm starting from Amazon Linux, and this is the very same Amazon Linux that you have on EC2 instances, but in a Docker container, in the latest version. I'm gonna create my home sdocs directory for sitting docs. That's the name of my app. Change the dir for that and copy everything on this directory from this Docker file to there, so it has my source code. I didn't need to copy everything. I could copy just what I need, but then I would have to cherry pick, and well, that would take a lot of time. So I'm just copying the whole source, installing Python 3, installing my app dependencies. In this case, it's just Flask, not much, not a lot, just Flask. And then I'm setting I just run this for debug purposes. I can easily remove this, not necessary. And this is with debug enabled. You can choose like if you want to debug your Python or not. I'll leave it on. And my source application file, the port that I'm exposing, and the entry point. So I'm running Flask on every host on the instance, and that's it. So I can Docker build. Uh, and this will build my container image and like build the file system starting from Amazon Linux, do all this step that I mentioned, create this nice little package that we call a Docker image, and then I can reuse this as is without having to change my infrastructure at all. I can just start as many copies of this small virtual machine as I'd like. So that's it. And it just takes a bit. And that it, there we go. And I can now run this on my own machine. So like this. with Docker run. So I tell Docker to run this image with this port. I ran the one I pushed to Docker Hub. This is on Docker Hub, by the way, if you guys want to try this image. But now I can run it anywhere. And on my machine, you can see that I have, let me show you guys. So localhost 5000 should work. Yay. And on fib, let's try the iterative version with x equal to 10. So we got 55. We could do 100 and get the Fibonacci for that. So this is how we run on the container. We did the same thing in many other ways. So we could run this same code as a Flask run. We could do the same thing as serverless. So here with, let me see if it's this one. We did SAM API local, SAM local. Well, we can check I would need to check the right command, but we can run the same thing serverless on the local machine using SAM local. That's the serverless application model. But now let's stick to containers so we don't lose the thread here. So now we were able to run this container on our own machine. Now we want to run this on the cloud and upload it and have it manage it for us. And there are two ways to do it, actually. So we can run containers on ECS. So ECS is Amazon Container Service for EC2. I have the ECS Flask container definition right here, and this is the CloudFormation template to run it on EC2 and ECS. So here we do the same trick, get the gallery ID for this container. We get, I set the key name, desired capacity, max size, and this is a bit of a large template. You can see I have a mapping for which AMI I want to use in each region and things like this. Let me go directly to the interesting part here. There's a task definition that says how our containers should be. So this is where I say the image that I want to run, how much memory I want to give this container, how much CPU, what are the logs, and things like this. How is the load balancer configured? So here you can see that I'm putting the load balancer inside those subnets that were created in the other stack. I have a listener mapping the port 80 to this target group. And in this target group, every request is mapped to the backend, the health checks, and so on and so forth. But you will see that we have two scaling criteria here. We have a EC2, ECS auto scaling group with the same subnets and an auto scaling launch configuration. And this will scale the underlying infrastructure of your containers. So the great idea behind containers is that you can manage the logic without managing the physical. So you can have 100 containers and distribute them in 2 really large instances, or in 10 smaller instances, or in 50 even smaller instances, or even in 100 instances, one with each container. So it allows you to decouple things and manage better. So if you have reserved instances, for example, this is pretty important. So you can consolidate, have higher utilization, reserve those instances, and save a lot of money. So you can see how that turns to money real quickly. And here we have a side code. There's just a side container, not not anything useful here. And the only trick that we have in this scaling for ECS here is this alarm that if we generate too many 500 HTTP requests, I also scale up. So this is kind of one way uh, to reduce errors. So if we're getting 500s, perhaps try to scale up may solve the issue. So this is quite a common thing to see in ECS, and that's the way to run it. And I have this already provisioned here in the same way, same scripts as we've been using. I just spared you the time. Let's just check the ECS Flask script. It's exactly the same thing. Define the names and run AWS CloudFormation deploy. AWS CloudFormation deploy will create this stack if it exists. If it does not exist, and update the stack if it already exists. So you could even type this directly. We don't even need a shell script for this. I'm just showing this one structure that I like again. And in the oh, Flask is the web server that we are using, like exposing our code to the web port, to the web container. I think I don't know if it's appropriate to call Flask the web framework or web server, but the web thingy in Python, one of the most popular for RESTful APIs is Flask. So when we are doing serverless, this is API gateway doing this job. When we are doing containers or instances, we need to spin up an application server or something similar to receive requests and invoke our code, right? And that's what this instance is doing. But the thing is, here we are responsible for setting these alarms. So you can see that this can change, and you have to do it on two levels because here we have tasks on the task definition. You define how each one of those is, and then there is a service definition. So if we go to the ECS service, this is how many of those tasks it will run. So it will run one of those tasks, and this is the task definition, and again the configuration for binding this to the load balancer. And although this is not a lot, like it's not so complicated, if you separate from the network part for everything and do it like this, a bit modularized and make this cross-stack references, the template itself is not really big. The hard issue here is that you have to think in two levels. You have to think how you're going to scale the physical part of your EC2 instances in the auto-scaling group, and how you're going to scale the logical part, how you're going to scale your service. And that's what the scalable target on application auto-scaling is doing here. We're going to dive a bit more into application load scaling in a little while. What I want to show you guys is Fargate, because Fargate removes this need to have it separated, these two layers of infrastructure. If you do have reserved instances and spot instances, and or if you need a specific resource in your EC2 instances, such as GPUs or FPGAs, this makes total sense. But for most apps, and this is probably what you guys want to do, so that's why I'm jumping forward to this, is not manage the infrastructure part, not manage the physical part. you just want to run your code probably. So this is much easier with Fargate, because with Fargate you can just tell here on our task definition, I can just say that this container needs this amount of CPU and this amount of memory, and there is no auto scaling group. So there is no launch configuration, there is no physical part to manage. All the physical part is going to be managed by Fargate. So we have to have these required capabilities on Fargate. They are more strict in terms of definition. You need to have network mode of AWS VPC. In your service, you have to define your VPC configuration. So if we check the service here, you need to have this network configuration section that we do not have in the ECS without Fargate, and define the launch type as Fargate. And that's pretty much all that's necessary to launch, to change your template to Fargate. But you can see that it makes it quite shorter and simpler to manage. This is one that I did now, but we can separate it even more and decouple things so it's even more isolated and don't have to change so much as you develop. And how will this one scale? How do we set the scaling parameters for this Fargate task? And now we're taking I'd like to show a bit of a different approach. We've been talking recently in the series about step scaling and simple scaling. When you do step scaling and simple scaling, you get to choose exactly how much you want to scale and when, and you create the alarms and you create the policies and so on and so forth. I'd like to show you guys today a different type of scaling that not everybody's used to, and this is target tracking. So here in this scaling policy that I'm creating here, I'm creating a CPU tracking scaling policy, meaning that I want my CPU, um, the CPU utilization. So I'm using a predefined metric here. You can define your own metrics, and there's a way to define your own metrics, but in our case, it's just a simple Fibonacci. So let's use CPU because our application is intensive on CPU. You could use memory, you could use errors, you can use any metric that you define, or one that's predefined by CloudWatch. So here in this case, we are using this predefined metric name. This is hard-coded, and it will be always this for CPU utilization, and it will take the average, and as the name says, it will match to 70%. So meaning that AWS will change my scaling target. This is the service that I'm referring to try its best to achieve average 70% CPU utilization. If it's below this, it won't do anything. If it's above it, it will trigger our auto scaling policy to run again and increase the amount of servers that we have, the tasks that we have to match, unless we are within 2 minutes. I don't want this to be too fast. Perhaps it takes a while for application to stabilize. So if it's under 2 minutes, I won't take other scaling actions. So this is a bit different when you use, again, just to recap, when we use step scaling and simple scaling, you're saying like how and when do you want it to scale up and down. When you do target tracking, AWS will create or shut down instances trying to maintain your predefined metric at the target value that you specify. So you still have control, and you can try and test what behaves better for your case, but this is very handy, so you don't have to create so many policies, right? And the dimension that this is going to change, like this is my scalable target definition. So when this policy is triggered, the desired count in my service, meaning the amount of tasks that are running behind the service, will increase up to the limit of 10. So, and as in Fargate, I don't need to worry about the physical part. This should run and scale much simpler. So let's take a look at that. In my Fargate, in my CloudFormation console, right here, I I have each of those stacks created, so you can see they all create and run fine. This is the Fargate Flask one that I just created, and the same idea holds true if I get the URL for my load balancer and do it just as I did on localhost. We should have exactly the same result, right? It's exactly the same code. And just to show you that this is really running, change to 1, and there we go, right? So you can see that this is running my app on my container, but I don't have to manage any of the underlying instances. I just tell Fargate how much CPU and memory I need, and voila, it's done. And on the management console, let's take a look at the ID here. It's 15 and 020. So let's go to the ECS console and see what it's doing there. So here we have the Fargate task definition and without Fargate. So here we have instances behind this. Here we don't have anything on EC2, just on Fargate. And you can mix and match how much you want on each side. You can even have both Fargate and EC2 tasks on the same cluster. Here I did it separate just for clarity, but again, each design may require different things. And let's take a look at the service. It have only one task here. The one task running on Fargate with this container definition. And on our auto-scaling rules, we can see we have two auto-scaling rules. One, target tracking, saying that we want to track ECS service average CPU utilization at 70 and keep it there, and that errors count. So if it starts erroring, I will add instances. So this is pretty much it. So let's go and start hitting it with some load. So I have EC2 instance running on my account. Let's take a look at it. So this is my sniper instance here. It's it's on the same code. Everything's going to be. I just want to shoot from internally from EC2, because if you do load testing from the outside, the network latency may influence your results, and it may be very hard to understand what you really see. So that, as a tip, I'd say you don't need like 128 cores or such a huge instance to load test. This is just because my account, I don't pay for it, but do mind that even if you use a smaller instance, it's good to do it from the inside, right? And I have here the same code. Oops, this is not, this is my local machine. So I have to SSH to the remote one. And I have the same code there. If my computer lets me log into this, I hope so. What's going on, my computer? Please help me. No terminal for me today. So let's quit it and start a new one. So back to where we were. By the way, this is called Glances. I really like this monitor. It shows you resource utilization and top, but with much better, much easier to see what's going on. So you know you're not overloading your load generator machine. I don't think that's the case today, but it may be useful. And in this other machine, in this other side, I will just start shooting. So in the sitting ducks directory, I have exactly the same code, and the the load test itself is defined by Gatling on source test Scala SDUX load tests. So this is how I'm doing load tests. I get the users and the ramp targets from environment variables and just start firing a few requests to each of my Fibonacci implementations to the hosts that I pass as targets. So in the end, our environment variables to trigger the load test. And again, if you don't, we did a bit of introduction to Gatling and to JMeter in previous episodes. Highly recommend, if you don't know Gatling, take a look at it. It's one of my favorite load generation tools. Highly recommended. It can be run as code, so don't need to handle like cranky UIs and things like this. It's your own code. You can do fors, whiles, repeats, ifs, any coding trick that you know you can just throw in there and make it part of your load test instead of being subject to whatever your load testing UI gives you. So this is very powerful for developers, and I highly recommend people to use testing tools like this. Well, but it's just a personal preference again. So on the on this script that we used on the past episode, I showed you how to set the environment variables, and I have those right here. So I pass the how many users I want, how long those are going to run, and the name of our task definition and the target that we're going to shoot against. And this is going to be mapped directly to the Gatling parameters on the test case. So yeah, that's probably too much load for our case, but that's the fun, right? We can increase this as much as we'd like. So let's pick our target, and on the output of our code formation, we can take the load target, and here it is. I will just reduce the amount of time so we don't spend so much time waiting for it. So instead of 10 minutes, I'm putting it 5 minutes. And instead of 2,000 users, let's do 5. So let's go faster and higher than we ever been before. And let's just double check that this is correct. Looks so. And I will set this on my sniper box and it's ready to shoot. So I can just run the Gatling command, which is SBT for Scala build tool. It will run the target called test only and run only this test case that I specified. You can have several in your project and things like this. So this is the command. And done. So hopefully now what's going to happen is this instance, which is pretty huge, is going to start firing lots of requests to our smaller instances if it was successful. So I forgot the HTTP in the URL, so let's do that again. Let's try that again. There is an HTTP missing here in target, so this must be a valid URL like this. And shoot. So yeah, so it's shooting, and you can. I will leave the output running. I can see that it's got some two handlers there, so it's okay. We will see some load on this machine naturally, and in CloudWatch, logs and templates, especially on ECS, we can see the effects of this load test going on. So let's take a look at our monitoring here. On metrics, we have CPU and memory utilization. I will open this in this new tab, and we can see CPU starting to raise. I will go for only 1 hour, so we can see it will go up and up as we go. Let's change the window to 30 seconds or something like this, and wait for the application to load to grow up. Because if you see the test case, the load testing SLS test case, this is the magic. I will ramp to the amount of users over this amount of time. So it will go up to those 5,000 users that I passed as a parameter over the 5 minutes that we specified. So 1,000 users per minute arriving at our app is pretty. It's pretty a huge, pretty steep curve, but I believe our app can make it. And here we're going to see it go. It's already on 41%. Our threshold is at 70%. So when we reach 70% CPU utilization on average, again, this is not instantaneous because it's always based on a metric over a period of time. So mind that it's not the one individual CPU, but the average on your whole cluster. So think about how that varies when you set up your metrics and your criteria for scaling. Here, the magic is all on the template. So let's take a look at that again. It's on this Fargate Flask. Here on the CPU tracking policy, I'm saying that when my service utilization is on 70%, that's my target. And setting this target is not so easy because if you go too tight, say you put like 99%, it will take too long for your application to scale. And by the time it scales, perhaps your traffic is already over you and it will take too long and you'll see errors and things like this. If it's too low, it may scale much before you really need it and cost you some extra money, but you're safer. So there is no magic here. It depends on how steep you want to be. You want to react. So if you want to react really quickly or safely, you need to set this really low and allow yourself time to grow, especially if your instances take a lot to boot and things like this. Or if they are fast and you feel comfortable, you can wait until you have like 90-95%. And this is something that only testing and testing over and over again can possibly tell you. But I guess you guys can see the benefit, especially if you've seen this before. If it was a step scaling or a simple scaling, you would need to create one policy to scale up, one policy to scale down, or perhaps more than one policy to scale up and more than one policy to scale down. And Amazon is Very we use a lot of mechanisms to do this, and having Amazon doing this on your behalf certainly take a lot of this from your hands. Let's see if our load is increasing. So we are already on 83, 81. So on our ACS, here we were with one desired count. Let's see if we reacted already. So our desired count is now two tasks, but only one is running because there was no time yet for the things to react as we are watching this live. And here in the tasks definition, we probably see one here provisioning and one running. So you see that as it scales, we see pending, and eventually it will be running, and more as long as we continue generating this load. So you can see that how much easier for us. So the it's so thinking it's not about redundancy. If we were talking redundancy, you would want to take a look here. So on the parameters for your scalable target, you could set this as minimum of two to have the redundancy, or you can start here your ECS cluster with at least two. The idea behind the 70% is how fast do you react, even if you have redundancy. So the higher you set your target, the longer it takes for you to react, which saves you money but may put you in danger. If you take a lower value, you are safer, you're scaling before, but you may waste some money scaling when you're not actually necessary. So it is a balance, not in the redundancy, but in how fast you react. And if we take a look at it again, we are already running in the two instances, and each of the requests is going to be distributed to a different instance because it's already added to the load balancer and so on and so forth. So here on the EC2 console, we can take a look at load balancers. And see, in this case, let's try to find out which one that is. So I'll have to check the group, the target group. So yeah, we have two IP addresses registered already, both healthy. Everything we're expecting working as expected with true health costs. And for as long as we keep uh, doing this and hitting this instance harder and harder, it will keep scaling. And as you can see in my response percentiles, we have much better results today than even we had with some serverless cases. See that we had 100% successes, zero errors, even with a very steep load, and just one request with latency above this 800 milliseconds threshold. That's the a very interesting result for us. So that's how we can make sure that our application reacts to the user as they come. And you see it's all defined in code. So if I want to deploy this again and again and again, I can just run these scripts and create as many environments of those as I'd like, and scaling very much simpler because we have application auto-scaling set up, and we still have a lot of control on our infrastructure, on our code, on how it runs, because it's all built by my own Docker file, so I can specify exactly how I want things. So that's what I'd like to show you guys today. You saw that if you're in between the instances and the functions, perhaps containers is a good idea for you. Or if you are already into containers and want to manage those with ECS instead of managing them by hand with Chef, Puppet, or your preferred config management tool, you can just deploy them with CloudFormation and Fargate, and you have the benefit that just like serverless, you can specify the amount of CPU and memory that you want and not have to worry about the physical part of instances as we needed on Beanstalk and again the trade-off against serverless, you have more control and precision, right? So that's it, and I hope you enjoyed today's broadcast. And in the next episode, we're going to add a database to this. And again, one very important point here is the concept of mechanical affinity. So now we saw how instances scale, how functions scale, how containers scale in the perspective of compute. So I hope that by now you can make an informed choice about what is better for you, because in some it's not like serverless is better than containers or containers are better than instances, but some cases, some apps will fit better on one of those mechanics. And now we have all at least one episode of each, and you have examples on how to do each one with CloudFormation. And now we can improve our application and doing not only Fibonacci but adding a database. And that's what you're going to see in the next episode of AWS Well Architected Solutions on Twitch. Thank you very much. See you next time.